Dear students, in this class I will be starting the fifth unit, that is semiconductor memories and the programmable logic devices. So in this unit we are going to study in digital systems how the data can be stored. That means we are going to discuss the memory devices which are used in the digital systems, and another one we are going to study programmable logic devices. These are the devices which can be programmed, and according to the user program, that devices are going to perform the functions. So two things we are going to discuss in the fifth unit, that is semiconductor memories and the programmable logic devices. So first I'll go with the semiconductor memories, and after that we will see the programmable logic devices. So first one, in implementing the digital systems, we will study the various subsystems such as input devices, processors, and the memory, registers, and the communication lines such as called as buses, and the output peripherals. If you take any digital system in the world which consists of all these things, for example, the best example for the digital system you can take that is a digital computer. If you take the computer, to give the input for the computer we require to have the keyboard or input devices such as keyboard, and from that keyboard we will be giving the input in the form of analog one, that is continuous signals, and it can't read that data, so that it requires to have the analog to digital one. So the digital data will be processed by the processor or the microprocessor, and primary results will be stored in the memory, and again it wait for the some more other primary results, and again they will store in the memory. That again both will be converted into the digital using the D2A converter, and after that we can study the output at the output devices such as monitor, printer, and like that we can have. So in an implementation of the digital system, I am going to explain what is the necessity of semiconductor memory. We have the various types of memories. Memory is nothing but it is a device which is used to store the data. Whatever you see in the mobile phones, if you take the pen drive or if you take the memory card, that memory card is used to store some data. That may be pics, videos, some PDF, some contacts, some word files, everything will be stored in that. So whenever we require that data, that can be accessed by the user, and that can be served as the immediate function by the memory device, and such that the memory is very important in the digital systems. We know that digital systems can be two types. One is a combinational circuit, another one is a sequential circuit. In sequential circuit we can make use the memory. Sequential circuit is a one in which output can be generated by making use of the previous input or the previous output values, past output values. So in order to have the past signals, that past signal has to store somewhere, and that past signal has to store somewhere, and that storing device is called as memory. Next one, array logic we are going to discuss. That is there are two array logics we have: programmable array logic and the logic arrays, and the CPLD, FPGAs. And in this array logic we are having, we can call these as PLDs. PLD stands for programmable logic device, and these programmable logic devices are 5 types. Programmable logic devices are 5 types. One is PROM, another one is PAL, another one is PLA, next one is about the CPLD, and the next one is about the FPGA. All these things we have to study in the 5th unit, such as semiconductor memories and 5 PLDs. So, and we are going to study one example, that is a microprocessor. It is the best example for the digital system. Microprocessor is nothing new, actually it is the CPU only. CPU stands for central processing unit. When you get the complete CPU on a single chip, that is called the microprocessor. So all these things we have to discuss in the presentation. Now I am going with the introduction. So in this lecture we will see the techniques used to implement the complex digital system. So here the point is very clear that we have been getting the digital systems on a single chip. That means the best example for that one is, if you take the CPU stands for central processing unit. We have been getting that central complete CPU on a single chip, that is called as microprocessor. That means each and every device in the CPU got reduced its size, so that we have been getting that CPU on a single chip, that is called as microprocessor. So microelectronics area allowed us to have the digital system in very small size. So then in this microelectronics era, every digital system has been replacing by its updated version of the digital system with the more features, like speed of the integrated circuit is more, and the size and cost of the integrated circuit is less compared to the previous one. So all these advantages can be possible if the integrated circuit size is small. As I just now given the example of the microprocessor, the microprocessor is nothing new, actually it is a CPU on a chip is called microprocessor. CPU, the entire CPU we can get on a single IC, that is called microprocessor. So CPU nothing but, again we can have that arithmetic logic units, register units, and the control unit we can have. All these things can be there in the single chip, that is integrated circuit. So all this microelectronics area, in the microelectronics era we have been getting the each and every digital system in a small size due to the one important law, that is called Moore's law. It's very important. Moore's law is nothing but, Moore's has given a theory that for every 1.5 year or for every 18 months, the size of the transistor would be half, or the number of transistors in any integrated circuit would be doubled for every 1.5 year or every 18 months. So surprisingly, this Moore's law has been working till today. So for every 1.5 year, for every 18 months, size of the transistor is reducing. If the size of the transistor reduces, then obviously the size of the integrated circuit is reduces. So by having this concept in the mind, we can imagine that if we are having the CPU on a chip in the 2021, if then what will be the CPU at the 2050? That means what? For every 18 months the size of the transistor getting reducing, so that IC size is going to reduce. So we can have the virtual processors also in coming days. There is a possibility to have the virtual processors also. Then next one, levels of integrations. This levels of integration explains us how the number of transistors has been increasing in a specific area as the level of integration varies. So this integration technology has started in the years of around 2012-30, and that by using the zero scale integration level, we can integrate only one transistor in a specified area. And later on we came across small scale integration that you can call as SSI, with the same size, on the same size of the integrated circuit. Now we integrated around 2 to 30 transistors, because this is at somewhere 1940s, this is at somewhere 1945s. So that as the years has been increasing, then the size of the transistor got reduced, so that there has a possibility to integrate the more number of transistors into the same area. Now we came across the medium scale integration, in short we can call that is MSI, that is in the years of 1960s. In this we have the again furthermore reduction transistor, size of the transistor, so that we had integrated more number of transistors on a same area. Next one is large scale integration, very large scale integration, ULSI, ultra large scale, giga scale integration, tera scale integration. So that means what? Now we are in the integration of tera scale. As per my knowledge, this one is also got updated with the nanotechnology. In a nanotechnology, the size of the transistor is enormously decreased, because the nanotechnology operates with the single electron transistor. In short, we can call them as SET, single electron transistor, SET. So that means what? Single electron, that in between the source and the drain, only channel can allows only single transistor at a time. That using that single transistor we are going to have the current, and that current is capable of achieving what the function we have been getting by making use of the various integrations levels. So we can get the same function with the single electron transistor also. That is the present research area that has been happening all over the world. Next one is about the Moore's law. Moore's law, as I just told, that Moore's law gives us the relation between the years and the size of the transistor, or the number of the transistors in a specific area. See this one? This is 1965, 1975, 80, 85, 90, 95, 2000, 2005, 2010. And even we have the more transistor 2015, 20, 21 also. So that means what? As the years has been increasing, the size of the transistors, that means the number of transistors that particular in the onto the that particular integrated circuit has been increasing. See this one. At 1965 to 1970, we have the processor that is called Intel 4004, and we have in between the 1975 to 1918, we had the 8086 microprocessor. So this is it is a Pentium 4 processor. Now we are at 2021, we are having the Qualcomm processor now onwards. So this is the Moore's law explanation. So this Moore's law is nothing that much important, and then I am going with the another one. This is now our unit name is about the semiconductor memories and the programmable logic devices. So memory is a device, physical device, which can be used to store the digital data. In the digital system, memory plays very important thing, because when you wanted to buy the mobile phone, when you wanted to buy the laptop, in the features we will ask the what is the internal memory and what up to the maximum it can be allowed. Like that we will ask the memory. So memory is very important device in any digital system, which is used to store the data. That stored data, whenever the user needed it, the user can access that one. Again, that can reside in the same place. So now I am going with the memory. So basically memories can be two types. One is a random access memory and the read-only memory. A random access memory, in short we can call as RAM, random access memory. It can have the two capabilities, that is read and write capabilities. That means for the user it can give the accessing of reading the data from this memory and the writing the data into this memory, that is called random access memory. So it is having the capability of read and write. Write is nothing but the user can save the data in that particular device. Write describes the process of storing the information. Read means we can take back, we can fetch the data from the device. RAM is a volatile memory in nature. That means if the sudden power guns also, that stores the as it is. So there are several forms of RAM are there. One is a static RAM, in short we can call SRAM. Next one is about dynamic RAM, in short we can call a DRAM. So initially we had the two memories. One is RAM and ROM. RAM stands for random access memory. ROM stands for read only memory. RAM can have the two capabilities, read and write. Reading is nothing but fetching the stored data from the memory. Writing is nothing but storing the new data into that memory, is called the writing. So there are two types of the RAM. One is static RAM and another one is the dynamic RAM. Static RAM uses the circuitry similar to the bistable multivibrator. Dynamic RAM uses the charge on capacitors every time it needs to the refreshing. So non-volatile memory means as long as power is there, that retains the information. Once the power is lost, it requires the power backup to store the memory. So anyway, RAM is a volatile memory, so that it stores the data even the power gone off. Next one is about the read-only memory. Read-only memory, the name itself it is suggesting that It can allows us to read the data from the memory only. We can fetch the data from the memory, but we cannot write the data into the memory. We cannot store the new data. So in generally read-only memory is used to store the instructions. Some set of instructions or programs can be stored in this memory. Program is nothing but what? It is the set of instructions. So it can be read, but it cannot write anything into the memory. Is inherently non-volatile, useful for programs, etc. Many forms we have. As compared to the RAM, we have the many forms from the ROM, such as PROM stands for programmable read-only memory, EPROM, that is electrical programmable memory or erasable programmable memory, EEPROM, that is electrically erasable programmable read-only memory. And next one is about the masked ROM, masked programmed ROM. So some are programmed by the manufacturer, such as called as masked programmed device. That means what? We cannot change that program. That program was installed by the manufacturer. That instructions will be stored in the memory is called as masked ROM. And others are user programmable. That means what? User can define some set of instructions that can be erasable and electrically erasable programmable read-only memories. Memory such as electrically erasable programmable read-only memory can be written, that is programmed as well as a read, but it is not RAM. It can be programmed relatively slow. As then this is a block diagram of memory organization. This is very, very important. Here, this is the VCC. Generally, VCC is about plus 5 volts for any digital IC. And here, this VCC is used for biasing of memory, or biasing is nothing but it makes complete on of that device. This is on now. So anyway, all the negatives will be grounded, and now we are having this is called as memory. This is called as memory, which is used to store the data in the binary. So now the thing is, in this memory we will be having some memory locations. It will be having some memory locations like this. Each memory location will be having an address. That address is called as physical address. Physical address is nothing but it is a combination of row address and the column address. Row address and the column address will define the physical address of a bit which is stored in the memory. So now we are having the address selection lines. As I said, this is having the memory locations. Each memory location will be having the physical address. Physical address will be with the row and the column addresses, and that row and column addresses will be defined by this address selection lines. Address selection lines. If it is having the n number of address, so that we can have inside 2 power of n memory locations. 2 power of n memory location. In each memory location, it is capable of storing the 1 byte of data, that is 8 bits. So these are the control lines. If you wanted to have the write data, that means what? If you wanted to write some data into this memory, this has to be active high, output enable. That means what? If we wanted to, this is write enable, this is read enable, we can also call. If you wanted to read the data from that, we can have this is output enable. Chip enable, that means what? To make the memory device is ready, we have to go for the chip enable. So now this will be interfaced with the input output devices. This memory will be interfaced with the input output devices. So input devices means what? Obviously that are keyboard, and from that keyboard we can give the data into the memory. And the output devices such as we can call some microprocessor, some other memory device, output peripheral memory device like the DMA, direct memory access, such that it can directly read the data from the memory. So once see this one, this arrow is there for the two sides, so that it is called, it is a bidirectional bus. It is called bidirectional bus. Bidirectional bus. Bus is nothing but it is a communication path which is used to carry the digital signals. So now this is the bus which is carrying the digital data between the memory and the input output device. It is a bidirectional one. It can take the data into the memory. It can fetch the data from the memory. So it can be bidirectional and it can be programmed. Next one. So that is about the memory. And coming to the array logic, such as called as 4 PLDs. PLD stands for programmable logic devices. These are the devices which can be programmed and which can function according to the program. So according to the program, these can make the function, and that program can be done by the programmer, that has nothing but a user only. Once the function for that program is done, we can erase that program such that we can write the new program. Program is nothing but giving the set of instructions to the digital system, that is called, it is a program. So that here we are giving the program, and according to that program our PLD is going to make the function, that is a programmable logic device will make a function, and after the completion of that function we can erase that program so that we can write the new program. Programmable, the word meaning programmable means it can be changed. So array logic will be divided into the two things. One is SPLD, simple programmable logic devices. Another one is a complex programmable logic devices. In complex programmable logic device, again we will be having the FPGA and CPL. In simple programmable logic devices, we have the three types. One is PROM, programmable read-only memory. Next one is PAL, programmable array logic. Next one is PLA, programmable logic array. These three things will come under the SPLD, simple programmable logic devices. Next two will comes under the complex programmable logic device such as CPLD and FPGA. So this is about the all the things. So now I am going with the next one, PLA, programmable logic array. It has array of inverters such as NOT gates, AND gates and OR gates. Can implement any logic function given limits on the number of inputs and outputs. So here PLA, programmable logic array, which is used to implement any Boolean function, but it will offer with the limited inputs and outputs only. It has the three primary gates such as NAND gates, NOR gate and NOT gates. So if we have the NAND gate, OR gate, NOT gate, we can realize any other Boolean expression, so that may be sum of product or the product of sum can be implemented by making use of PLA. So this is the PLA. See this one. Just now we explained it can have the NOT gates. See this one. This is the NOT gates. This is NOT array. Next one, it is having the AND array. This is AND array. Next one, it is having the OR array. NOT gates, AND gates, OR gates. So then you can go with the example. X is equals to A bar, B bar, C bar, D plus A bar, B bar, C, D. Go with the X now. X, see this one. X is equals to A bar, B bar, C bar, D bar. This is this one and this one. And finally it is a sum of products, so that you can have this one. So in PLA structure, we must remember that in a PLA structure, we can have the array of NOT gates. Array is nothing but it is a group of similar things is called array. Array of NOT gates we have. Array of AND gates we have. Array of NOT gates, OR gates we have, so that can be used to implement sum of product. Next we can go with the PLA program. PLA. So this one required things. See this one. What we require to have, X is equals to A bar, B bar, C bar, D. A bar, B bar, C, D. A, B, C, D bar. So in the previous case, we have used all the things. We have used all the things and connected, and wherever that is one is there, that is only that is accepted. But here in a programmable logic device, the complexity of the circuit got reduced. Whichever we needed, that line only we have been using, such that it is connected to the output side. That means what? By making use of the user program, we can reduce the complexity of the circuit, such that we can reduce the hardware of a digital system also. The next one is field programmable gate arrays, FPGA. We can call, in short, we can call it is FPGA, in short, field programmable gate array. So we will have some programmable fields in which each programmable field can act as input output devices or any one PLD that can act as a PLD. Now we are having the block diagram of the field programmable gate array FPGA. A programmable device using more complex cells. See this one, these are the more complex cells, input output devices. Programmable cells, these are programmable, and these are the programmable interconnections. Everything is there. Programmable cell is nothing but this may be any PLD. PLD nothing but what? Programmable logic device, that may be PROM. We can call PLA, we can call, and PAL we can. So this cell can be programmable. This cell can be programmable. According to the user program, this cell can be programmed. So once it got programmed, to drive that into the output, again we have to program the interconnection. These wires are there, right? This is horizontal and the vertical wires are there. These are called as a switch box. It is a switch box. These are horizontal connecting wires, and these are the vertical connecting wires. These also programmed by the program. So finally we can have the output from the input output cells. This is about CPE and FPGA. Then just now I have explained the microprocessor. Microprocessor is a digital system which accepts the input in the form of digital, and it processes the data and it delivers the output in the form of the familiar data. So now see this one, microprocessor based system. It is a CPU. CPU is also called as microprocessor. When the central processing unit is available on a single chip, then that is called as microprocessor. Micro means small, processor which is used to process the data. From the input we will be giving the input that will be processed, and to process that input data, or whatever the input has given, based on that input, if the processor needs some more information or some instructions from the memory, and that can be taken by the processor from the memory, so that instructions will work on this data such that it delivers the output. So now see this one, it is a bidirectional one. That means what? This CPU can write the data into the memory, and CPU can read the data from the memory. This is the bidirectional one. So this is about the microprocessor based system block diagram. So communication within the processor, we know that communication, how the signals can be transmitted from the block to block, that is about the microcomputer. Microcomputer on a single chip is called as it is a microcontroller. Microprocessor is different and the microcontroller is different. Microprocessor is nothing but central processing unit on a single chip is called the processor. But if the computer is on a chip is called the microcomputer or the microcontroller. So this is the best example for the communication within the process microcontroller. Inputs, central processing unit, this is now the processor it is. Memory, input. If all these things are available on a single chip, that is called a microcontroller or the microcomputer. See this one? This microprocessor and the microcontroller will have the 3 buses. Bus is nothing but it is a communication medium which is used to transmit the digital signal. Data bus, which is used to carry the data signals. Address bus, which is used to define the particular address. From that we can fetch the processor can fetch the data, or onto that location, onto that address, the processor will write some more data. Control bus, that operation of the data is completely controlled by the control bus. This is about the microcontroller or the microcomputers. Then registers, all these things we don't have in the syllabus. Then in the next class I am going to cover the PLDs in depth, such that this unit will be closed. Thank you students. Thank you so much, and try to write the notes from this material.